The Stern-Gerlach experiment was a groundbreaking scientific investigation conducted in 1922 by Otto Stern and Walther Gerlach, two German physicists who were determined to test a very specific ideal about the behavior of atoms in magnetic fields. At first glance, their setup looked simple: a small furnace, a beam of atoms, a non-uniform magnetic field, and a metal plate to catch the atoms. But hidden within this simplicity was a profoundly deep question, one that would transform physics forever. To understand what the experiment actually was, why it mattered, and what it revealed, we must explore the nature of atoms, magnetism, classical physics expectations, and how a small silver atom became the center of one of the most important discoveries in quantum science. The experiment was designed to test whether the magnetic properties of atoms behaved in a continuous way or in a quantized way. In classical physics, atoms could be imagined as tiny spinning magnets, similar to how the Earth behaves with its magnetic poles. If you place millions of these tiny magnetic compasses into a magnetic field, they would orient themselves in a multitude of directions, depending on their initial states. Because of this, if you sent a beam of such atoms through a magnetic field that is stronger on one side than the other, the beam should gradually spread out, landing on the detector screen as a continuous streak representing all the possible orientations of the atomic magnets. This classical expectation is what Stern and Gerlach set out to test, but they wanted to test it at a level of precision no one had attempted before. Their underlying motivation came from newly forming ideas in early quantum theory, particularly the suggestion by Niels Bohr and Arnold Sommerfeld that the angular momentum of electrons might have quantized values. But this idea was still theoretical and controversial because there was no direct experimental method to test it. Stern proposed that a beam of atoms could be used for such a test. If the magnetic orientations of the atoms were truly quantized, the beam would not spread out smoothly. Instead, it would split into a small number of distinct points. If the beam did split, that would mean nature was not continuous at the smallest scales, something classical physics could not explain. To conduct the experiment, they chose silver atoms. Silver was ideal because it has a single outer electron that determines its magnetic behavior, and this electron has an angular momentum that should produce a magnetic moment. Also, when silver is heated, it vaporizes cleanly without reacting or producing complex molecules. The experiment began with a furnace heating silver metal to a high enough temperature to create a vapor of silver atoms. These atoms were released through a narrow slit, forming a thin beam traveling in one direction. This beam then passed through an inhomogeneous magnetic field created by a specially shaped magnet. The magnetic field was intentionally stronger on one side than the other, meaning that atoms with different magnetic orientations would be deflected differently. The core idea was simple. If the atoms had magnetic moments pointing in random directions, like tiny compass needles, the beam would fan out smoothly on the detector plate. Stern and Gerlach expected to see a symmetrical spread, perhaps a curved region where the silver atoms would land in positions corresponding to the different orientations of their magnetic moments. But this classical prediction did not take into account the developing concept of quantization, an idea that was still mysterious and incomplete at the time. As the beam of silver atoms passed through the non-uniform magnetic field, something completely unexpected happened. Instead of forming a continuous smear, the beam split cleanly into two distinct spots on the photographic plate. These two spots meant something astonishing. The atoms did not orient themselves in a continuous range of angles. They had only two allowable orientations, up or down. There were no atoms landing in between, indicating that the magnetic moment of the atoms was quantized. It could only take discrete values, not a continuous range. This discovery challenged the foundations of classical physics. It was the first direct experimental evidence that microscopic properties of particles come in quantized states, not smooth ones. The Stern-Gerlach experiment was therefore not just a test of a theoretical idea. It was an experimental revelation that forced physicists to rethink what atoms really are. Before the experiment, many scientists still believed in classical ideas like continuous trajectories, classical orbits, and smooth distributions. After the experiment, these beliefs could no longer stand unchallenged. The experiment proved that the behavior of atoms cannot be described by classical mechanics alone. Instead, it required a new understanding, an understanding that would eventually become quantum mechanics. What made this experiment especially remarkable is that Stern and Gerlach did not know they were discovering quantum spin. At the time, the concept of electron spin had not yet been invented. The idea of spin, a quantum property indicating that electrons behave as if they are spinning particles with intrinsic angular momentum, would only be proposed a few years later by Samuel Gaudsmit and George Uhlenbeck in 1925. Yet the Stern-Gerlach experiment had already revealed the consequences of this unknown property. The splitting of the beam into two parts was a direct result of the electron's spin being quantized into two states. But because spin had not been formally introduced, Stern and Gerlach interpreted the results in terms of orbital angular momentum. Their experiment was ahead of its time. It gave an answer before physicists even knew what question they were asking. To understand exactly what the experiment was, it is important to visualize the physical setup. The furnace produced a beam of silver atoms that traveled in a straight line. The atoms then entered a region where they encountered an inhomogeneous magnetic field. This magnetic field had a gradient stronger at the top and weaker at the bottom. Because the magnetic moment of the atoms interacts with this gradient, the atoms experienced a force. If the magnetic moment pointed upward, the atom was pushed upward. If the magnetic moment pointed downward, the atom was pushed downward. But if the magnetic moment was at some angle between up and down, classical physics predicted that the atom would be deflected only slightly, in proportion to its orientation. This classical prediction would create a continuous distribution of impacts on the detector. Instead, only two impacts appeared on the plate. This result showed that the magnetic moment could not take intermediate values. It had to be either spin up or spin down. Thus, the experiment was a direct demonstration of quantum two-state systems, long before the concept of a qubit in quantum computing existed. In fact, the Stern-Gerlach experiment can be understood as the earliest physical realization of what would later be called a quantum measurement. The experiment forced the atom to choose one of the two spin states, collapsing the quantum wave function into one of the possible outcomes. The experiment also showed that the act of measurement itself plays a crucial role in determining the behavior of quantum particles. Before passing through the magnetic field, each atom existed in a quantum superposition of spin states. It was not up or down until the magnetic field forced it into one of the two possibilities. This idea was completely foreign to classical thinking, where objects always have definite properties independent of whether they are being measured. The Stern-Gerlach experiment demonstrated that quantum properties do not have definite values until they are observed or measured. This result would later influence the interpretation of quantum mechanics, especially through the contributions of Niels Bohr and Werner Heisenberg. Another important aspect of the experiment is that it required extremely careful engineering to work properly. The silver atoms had to travel in a vacuum to avoid collisions with air molecules. The furnace needed to produce a stable beam. The magnetic field had to be precisely shaped to create the correct gradient. The detector had to be sensitive enough to record the tiny impacts of individual atoms. Every detail mattered because the effect being measured was very small. If the magnetic field had been poorly designed or the beam too wide, the results would have been blurred and the quantization might not have been visible. The experiment's success was not accidental. It was due to precise design, discipline, and a willingness to attempt something no one else had tried. Stern initially proposed the experiment in 1921, inspired by the idea of testing space quantization. Gerlach, who had experience with magnetic measurements and experimental apparatus, joined him to bring the idea to life. Together, they created one of the most elegant and powerful experiments in modern physics. The apparatus was small enough to sit on a laboratory table, yet the implications of its results would reshape scientific understanding across the world. The experiment was not expensive, not complicated by today's standards, and not dependent on advanced technology. But what it revealed was profound. The world at the smallest scales behaves according to rules fundamentally different from those of classical physics. Thus, the Stern-Gerlach experiment was, at its core, a test of how atoms behave in magnetic fields. But it became much more than that. It became the first clear demonstration of quantum state quantization, the precursor to the idea of spin, and one of the earliest experiments to show the connection between measurement and quantum state collapse. It was the moment when physicists were forced to confront the strange, discontinuous nature of the quantum world. The experiment stands as a symbol of how simple ideas can uncover deep truths about reality. It changed the direction of physics, influenced the development of quantum mechanics, and laid the foundation for modern technologies such as magnetic resonance imaging, atomic clocks, and quantum computers. In summary, the Stern-Gerlach experiment was a bold and elegant test of a fundamental question in physics. Do atoms behave like classical objects or quantum objects? By shooting silver atoms through a magnetic field and observing how they split into two beams, Stern and Gerlach proved that atoms do not follow classical rules. They obey quantum rules. Their magnetic properties are quantized, not continuous. The experiment revealed the existence of discrete spin states long before the concept of spin was formally introduced. In doing so, it opened the door to the quantum revolution. It marked the shift from the classical world, you to the quantum world, you, and showed that the tiniest particles in nature do not behave in ways we expect from our everyday experience. Instead, they follow the counterintuitive but precise laws of quantum mechanics, a discovery that would reshape science and technology for the next 100 years. The Stern-Gerlach experiment, when viewed from the perspective of the years that followed, appears almost prophetic. It not only revealed a fundamental quantum behavior, but also hinted at deeper layers of nature that physicists had not yet discovered. To complete an in-depth understanding of what the experiment truly was, we must look at the experiment historically, scientifically, and conceptually. At the surface level, it was simply an apparatus that passed silver atoms through a magnetic field. But understanding what this experiment was also requires exploring its deeper meaning, what it tested, why its results were surprising, how the apparatus worked in detail, what assumptions were overturned, and how it ultimately shaped the way quantum mechanics is understood today. To understand what the experiment was, it is essential to imagine what scientists believed before it took place. Around 1920, classical physics had been astonishingly successful. Newton's laws described motion with incredible accuracy. Maxwell's equations explained electricity and magnetism. Thermodynamics described heat, energy, and matter. Many scientists assumed that soon, all remaining mysteries would be solved through classical equations. But there were early warning signs that the classical world was incomplete. The photoelectric effect, blackbody radiation, atomic spectra, and the structure of atoms all resisted classical explanation. Still, even with these anomalies, the idea that something as basic as an atom's magnetic behavior might be quantized seemed radical. In classical physics, angular momentum and magnetic moments are continuous. A spinning top, a planet, or a bar magnet can be oriented in any possible direction. There are infinite intermediate orientations. If atoms behaved the same way, the beam of silver atoms should show a continuous blur on the detector. This belief influenced the early criticism of quantum theory. Many physicists found quantization hard to accept because it contradicted intuition. Quantization seemed like a mathematical trick rather than a physical truth. It was in this climate of uncertainty that Otto Stern proposed an experiment to directly test whether space quantization, discrete orientations of angular momentum, was real. Thus, the Stern-Gerlach experiment was an attempt to see whether nature at the atomic scale behaved in terms of discrete states or continuous states. That was the central purpose of the experiment. The discovery itself, 2 distinct spots, was astonishing not only because it contradicted classical expectations, but also because it confirmed the reality of quantum states. Before the experiment, quantization was an abstract idea used to calculate atomic spectra. After the experiment, quantization became a physical truth that left a mark on photographic plates. It was no longer a mathematical convenience. It was a feature of nature. To understand the experiment further, it helps to imagine the silver atoms themselves. Silver has 47 electrons, but only one. Its outermost electron determines its magnetic behavior. This electron has an intrinsic angular momentum, and therefore a magnetic moment, that interacts with magnetic fields. When the atom travels through the magnetic field gradient in the Stern-Gerlach setup, the force it experiences is proportional to the orientation of this magnetic moment. In classical physics, this orientation is random and continuous. In quantum physics, it is quantized. The magnetic field used in the experiment was not uniform. One side of the magnet was shaped like a wedge to create a strong gradient, meaning the magnetic field was much stronger in one direction. This gradient is essential because a uniform magnetic field would merely change the atom's orientation, not its trajectory. A gradient applies a different force depending on the direction of the atom's magnetic moment. Thus, the magnetic field acted like a spin sorter. Atoms with spin pointing upward were pushed upward. Atoms with spin pointing downward were pushed downward. No intermediate forces were observed because no intermediate spin states existed. In the actual experiment, the deflection was incredibly small, fractions of a millimeter. But over the distance the atoms traveled, this small angle became separable enough to distinguish 2 spots. Stern and Gerlach used a photographic plate coated with a thin film that would darken when silver atoms struck it. When the experiment was run, they observed, after developing the plate, 2 separate dark bands. This result was so striking that it immediately became one of the most important experimental observations in modern physics. But understanding what the experiment was also requires understanding what it did not show. It did not reveal electrons spin directly. It did not explain why the angular momentum was quantized. It did not measure the spin value of a half that would later become essential in quantum mechanics. Instead, the experiment demonstrated a phenomenon that was mysterious at the time. Atoms behaved as if their magnetic moments could adopt only a limited number of orientations. The correct explanation, electron spin, was proposed only after the experiment was completed. Nonetheless, the experiment itself provided the empirical evidence needed to justify this new idea. It was the ground on which later theories were built. The Stern-Gerlach experiment also raised philosophical questions that would fuel debates for decades. One such question was, what determines whether an atom goes to the upper spot or the lower spot? If classical physics were correct, the atom's orientation before entering the magnetic field would determine the outcome. But quantum physics suggested something more subtle. Before measurement, the atom exists in a superposition of spin states. Only when it encounters the magnetic field, which acts as a measuring device, is the atom forced to choose a definite state. This idea that the act of measurement creates the outcome was deeply unsettling for many physicists, including Einstein. Einstein famously criticized the idea that nature behaved probabilistically, saying, "God does not play dice with the universe." The Stern-Gerlach experiment, however, seemed to show that the universe indeed behaves probabilistically. The experiment was therefore not just a technical demonstration. It was a philosophical challenge to classical determinism. It revealed a world where outcomes are inherently uncertain until measured. Another important aspect of understanding what the Stern-Gerlach experiment was is recognizing that it became a template for modern quantum experiments. Today, physicists use similar concepts in experiments involving trapped ions, polarized beams, spin filters, and quantum bits in quantum computers. The idea that quantum states can be separated, measured, or manipulated based on their spin is fundamental in quantum information science. By passing through a magnetic gradient, a quantum state is projected into one of its basis states. This is exactly how qubits in quantum computers are initialized or measured. They collapse into one of two possible outcomes. In this sense, the Stern-Gerlach experiment was the first experiment to operationalize the mathematical concept of a two-state quantum system. It created a physical demonstration of what would eventually become the most basic element of quantum information, a system with two discrete states that can be measured, manipulated, and analyzed. Thus, what the experiment was extends beyond its historical moment. It was the beginning of a practical understanding of quantum states. The experiment also influenced the development of quantum mechanics in direct ways. The result motivated theorists like Bohr and Sommerfeld to refine their models of atomic structure. The discovery of discrete splitting reinforced the need for a quantum theory of angular momentum. And later, after electron spin was proposed, the experiment became a key piece of evidence supporting the existence of intrinsic angular momentum. The implications radiated outward, from atomic physics to nuclear physics, chemistry, spectroscopy, and eventually condensed matter physics. When physicists describe what the Stern-Gerlach experiment was, they often emphasize how simple the apparatus appeared. But this simplicity should not hide the depth of the discovery. The experiment was simple only in appearance. Its conceptual implications were enormous. It told scientists that the smallest building blocks of matter behave in ways that defy classical logic. Atoms do not behave like tiny planets orbiting a nucleus. They do not have continuously variable orientations. They do not carry deterministic trajectories through space. Instead, they inhabit a quantum world where states are discrete, outcomes are probabilistic, and measurements are fundamental. A deeper way to understand what the experiment was is to consider it as a story of curiosity and courage. Stern and Gerlach were not famous physicists at the time. Their experiment was not funded by large institutions or elaborate programs. It was a bold attempt to answer a question that many physicists considered too uncertain or risky to pursue. The success of the experiment proved that simple, well-designed experiments can reveal truths about the universe that no amount of theoretical speculation can uncover. In this sense, the experiment was a triumph of scientific methodology. The idea that nature reveals her secrets when questions are asked in the right way. What the experiment was, fundamentally, is a direct observation of quantum behavior manifesting on a macroscopic scale. The dark spots on the photographic plate were visible to the naked eye. They were not abstract symbols in an equation. They were physical imprints showing that atoms had chosen distinct paths due to their quantum states. This merging of the microscopic and macroscopic worlds was profound. It showed that quantum phenomena are not confined to small scales. They can have observable consequences in everyday physical objects. Another way to appreciate what the experiment was is to consider its legacy. The experiment is still taught to every physics student because it captures the essence of quantum mechanics with extreme clarity. It shows that quantum states are discrete. It shows that measurements change systems. It shows that the world at small scales does not follow classical intuition. It is a clean, elegant demonstration that stands at the heart of quantum physics. The experiment's legacy extends into technology as well. Magnetic resonance imaging MRI, for example, works by exploiting the spin of nuclei in a magnetic field. The basic idea, spin alignment and separation in a gradient, is directly related to the Stern-Gerlach effect. Atomic clocks rely on transitions between spin states. Quantum computers use spin states as qubits. All of this traces back to the simple but profound question asked by Stern and Gerlach: do atoms behave classically or quantum mechanically? Finally, to understand fully what the Stern-Gerlach experiment was, one must understand that it was a turning point. Before it, quantum theory was a patchwork of ideas struggling against classical tradition. After it, quantum theory had undeniable experimental support. The experiment was a bridge from the old world to the new world, from classical determinism to quantum probabilities. It revealed that the structure of reality itself is quantized. It revolutionized physics not by being complex, but by being clear. In its essence, the experiment was a question posed to nature. Do atoms obey classical laws, or do they obey quantum laws? And nature answered loudly and unmistakably. The beam split. Two spots appeared, and with that, the classical world gave way to the quantum world. The choice of silver atoms in the Stern-Gerlach experiment was not arbitrary, but a carefully considered decision shaped by the physics of the time, the experimental design, and the properties of silver itself. Understanding why silver was selected requires a deep look into the experimental goals, the characteristics of atomic structure, the nature of magnetic interactions, and the practical considerations of conducting a precision experiment in the early 20th century. This exploration reveals that the choice of silver was both strategic and necessary to achieve the groundbreaking results that Stern and Gerlach obtained. At the core of the experiment was the need to observe the effect of a magnetic field on individual atoms. The underlying question they sought to answer was whether atomic magnetic moments were continuous or quantized. To answer this, The experimentalists needed atoms that could produce a clear and measurable deflection in a magnetic field. Not all atoms are equally suitable for such an experiment. Factors such as the number of electrons, the arrangement of their orbits, the stability of the atomic vapor, and the magnetic properties of the atom all influence the feasibility of observing discrete quantum effects. Silver emerged as a uniquely favorable candidate when these factors were considered together. Silver has 47 electrons, and its electronic configuration ends with a single electron in the outermost shell, specifically in the 5s orbital. This is crucial because the magnetic properties of an atom largely depend on its unpaired electrons. In classical terms, each electron generates a magnetic moment due to its orbit and intrinsic spin. Atoms with multiple unpaired electrons or complex configurations tend to have more complicated magnetic interactions that could obscure the results of an experiment like Stern-Gerlach. By contrast, silver's single outer electron ensures that its magnetic moment is well defined and relatively simple. This simplicity was essential for producing a clear, interpretable splitting pattern when the atoms pass through the non-uniform magnetic field. The magnetic moment of the atom, created by the electron, interacts with the gradient of the magnetic field. If the magnetic moment is quantized, then the force it experiences in the field will be discrete, leading to distinct deflections. Choosing an atom with a single, unpaired electron maximizes the likelihood that the experiment will reveal a simple binary splitting rather than a more complex pattern that could be difficult to interpret. Silver, therefore, offered the ideal combination of having a measurable magnetic moment and simplicity in interpretation. This single unpaired electron was essentially the signal that Stern and Gerlach needed to observe the quantization phenomenon directly. Another reason silver was chosen relates to practical experimental considerations. The Stern-Gerlach experiment required a beam of neutral atoms traveling in a vacuum. To achieve this, the experimenters needed a substance that could be vaporized efficiently without decomposing or reacting chemically. Silver metal has a relatively low vapor pressure at elevated temperatures, meaning it can be heated to produce a steady stream of atoms without forming unwanted compounds. Many other elements either oxidize rapidly, decompose when heated, or have low vapor pressures, making it difficult to generate a consistent atomic beam. Silver's stability under heating conditions made it ideal for producing a controlled, uniform beam of atoms suitable for the precision measurements required. The atomic mass of silver also played a role in its selection. With an atomic mass of about 108 U, silver atoms are sufficiently heavy to travel in straight trajectories without being deflected by minor perturbations, yet not so heavy as to make the experiment impractical. Lighter atoms could be scattered by residual gas molecules in the vacuum chamber or by thermal motions, making the beam less precise. Heavier atoms would require stronger magnetic fields to produce the same degree of deflection. Silver's intermediate mass was well suited to produce observable deflections with the magnetic field strengths that Stern and Gerlach could generate in the laboratory at the time. From a quantum perspective, silver's atomic structure offered another advantage. Its single valence electron means that its orbital angular momentum in the ground state is zero. This is important because the observed splitting in the experiment was primarily due to the electron's intrinsic spin, rather than orbital motion. Had they chosen an atom with significant orbital angular momentum in the ground state, the resulting pattern would have been more complicated, with multiple splits corresponding to different orientations of the orbital motion combined with spin. By using silver, Stern and Gerlach effectively isolated the effect of spin, which was unknown at the time, making the observed two-spot pattern more easily interpretable. The production of a monoatomic beam was another critical consideration. For the Stern-Gerlach experiment to succeed, the beam needed to consist of individual, isolated atoms rather than clusters or molecules. Molecular beams or clusters could behave unpredictably in a magnetic field, and the resulting deflection patterns could become smeared or unrecognizable. Silver atoms, when vaporized, readily form monoatomic beams under the conditions used in the experiment. This ensured that each atom behaved independently in the magnetic field, producing a clean experimental outcome that could be analyzed accurately. Experimental reproducibility was also a key factor in choosing silver. Physics experiments require consistent and repeatable results, particularly when testing fundamental hypotheses about the nature of reality. The properties of silver allowed Stern and Gerlach to produce multiple beams under controlled conditions, ensuring that their observations could be confirmed across several trials. Consistency in beam intensity, deflection pattern, and detection was crucial to convince the scientific community that the results were genuine and not artifacts of experimental error. It is also important to consider the historical context of the experiment. At the time, several candidate elements could have been chosen, such as alkali metals like sodium or potassium, which also have a single valence electron. However, many of these elements are highly reactive, especially at elevated temperatures, and pose greater challenges for maintaining a clean vacuum environment. Silver, being chemically stable and non-reactive, reduced the risk of contamination and technical complications. Its choice reflects the careful balance that experimentalists must maintain between theoretical suitability and practical feasibility. Furthermore, silver atoms produce a clear signal on the detection medium used by Stern and Gerlach. When the atoms struck the photographic plate or film, they formed distinct marks due to the deposition of silver. This direct visualization was crucial. Other atoms, particularly gases or volatile elements, might not have produced such a clear or permanent imprint. Silver's inherent ability to create visible marks allowed the experimental results to be recorded reliably and studied in detail after the beam passed through the magnetic field. This contributed to the undeniable clarity of the two-spot result that confirmed quantization. Another subtle but important factor is related to temperature management. Heating the atoms to produce a beam introduces thermal motion, which could blur the deflection pattern. The relatively high atomic mass of silver mitigates this effect, as heavier atoms move more slowly at a given temperature compared to lighter atoms. This means that the beam could remain narrow and well collimated over the experimental distance, allowing precise observation of the discrete deflections caused by the magnetic field. The combination of vaporization characteristics, atomic mass, and magnetic properties made silver uniquely suitable in this regard. The choice of silver also reveals the interplay between experimental design and theoretical expectation. Stern and Gerlach were aware that quantization might produce a subtle effect, so they needed an element where the effect would be amplified enough to be observable. Silver provided a balance. The magnetic moment of the single valence electron was strong enough to interact noticeably with the gradient in the magnetic field, while the absence of complicating orbital contributions simplified the interpretation. The experiment was therefore designed to maximize signal and minimize noise, and silver was the ideal atom to achieve that balance. In summary, silver atoms were used in the Stern-Gerlach experiment because they offered a perfect combination of theoretical simplicity, magnetic clarity, experimental practicality, and observational reliability. Their single valence electron allowed the clean observation of quantized magnetic moments. Their stability under heating and non-reactive nature made them experimentally feasible. Their mass ensured beam coherence, and their ability to leave visible marks on detection media allowed for clear, unambiguous results. Without these properties, the experiment might have produced confusing, irreproducible, or uninterpretable data. In this sense, the choice of silver was not merely convenient. It was essential. It enabled Stern and Gerlach to produce the first direct evidence of quantum behavior in atoms, paving the way for modern quantum mechanics and the understanding of intrinsic spin. The significance of silver's role goes beyond the experiment itself. It demonstrates how careful selection of materials can make the difference between an ordinary experiment and a revolutionary discovery. Stern and Gerlach's insight in choosing silver reflects the precision and foresight necessary for fundamental physics research. Their experiment shows that the right element, combined with an ingenious setup, can uncover the hidden rules of nature that are invisible to classical intuition. Silver, in this context, was not just a chemical element. It was the key to unlocking a window into the quantum world. Continuing the exploration of why silver atoms were chosen for the Stern-Gerlach experiment, it is essential to recognize that the choice also reflects an understanding of the interaction between atomic structure and measurement sensitivity. Stern and Gerlach needed a system in which the effect of the magnetic field would be measurable yet unambiguous. Atoms with multiple unpaired electrons or complex nuclear configurations could have generated overlapping or multiple deflections that would confuse the interpretation. Silver, with its single valence electron and minimal orbital angular momentum, presented a near-ideal system where the measurement could be directly linked to fundamental quantum properties, even if those properties like electron spin were not yet fully understood. From a physics standpoint, the quantization of the magnetic moment was expected to produce observable deflection only if the magnetic force acting on the atom was significant relative to the thermal motion of the particles. If the atoms were too light or the magnetic moment too weak, thermal velocities would dominate, and the discrete splitting might be lost in random motion. Silver's atomic mass provided just the right balance, heavy enough to maintain a stable trajectory through the experimental apparatus, yet light enough to experience noticeable deflection under the magnetic gradient available in the laboratory. This balance made the deflection measurable with the technology of the 1920s and ensured the clarity of the two-spot result that would confirm quantization. Moreover, the use of silver demonstrates the foresight Stern and Gerlach had regarding experimental reproducibility. High-quality experiments require materials that behave consistently under repeated trials. Silver, being chemically inert and structurally stable, reduced the likelihood of contamination or unpredictable chemical reactions during heating. Other candidate elements, particularly alkali metals like sodium or potassium, are far more reactive and could have complicated the experiment through oxidation or uncontrolled interactions with the vacuum chamber. The reliability of silver ensured that the critical splitting effect could be observed repeatedly, solidifying the experimental claim and earning trust within the scientific community. The clarity of the deflection pattern in the Stern-Gerlach experiment also relied heavily on silver's atomic structure. As previously noted, silver's single outer electron allows for a clear magnetic moment arising primarily from spin, without the confounding effects of orbital angular momentum. Had a more complex atom been chosen, the resulting pattern might have been multi-branched, with contributions from both spin and orbital effects. Such complexity could have obscured the fundamental quantization phenomenon, delaying the discovery or making the results subject to dispute. By selecting silver, Stern and Gerlach effectively simplified the system to its essential quantum behavior, allowing the experiment to highlight the underlying principle of discrete spin states. Additionally, silver's vaporization characteristics were crucial to forming a narrow, collimated atomic beam. The experiment required atoms to travel in straight lines without colliding with other particles or deviating due to turbulence. When silver is heated in a vacuum, it produces a beam of neutral, monoatomic particles suitable for the magnetic field to act upon. The beam's stability was vital. Even small deviations in trajectory could have smeared the deflection pattern, reducing the contrast between discrete outcomes and making the observation of quantization ambiguous. The physical and chemical properties of silver allowed for a beam that met these stringent requirements. Silver's role as a visual marker should not be underestimated. The experiment depended on detecting where the atoms landed after passing through the magnetic field. Photographic plates were coated to reveal the positions of the atoms, and silver itself left clear, visible marks. Other elements might have required chemical development or more complex detection methods, introducing potential sources of error. Silver's natural visibility ensured that the splitting could be observed unambiguously, reinforcing the experimental result and allowing Stern and Gerlach to present compelling evidence for the existence of quantized states. Furthermore, silver's isotopic composition contributed indirectly to the experiment's effectiveness. Silver has two stable isotopes, both with nuclear spin values that do not interfere with the splitting of the beam in the magnetic field. While isotopic effects are subtle, their consistency ensured that the beam's deflection pattern remained straightforward, without introducing additional variability that could complicate interpretation. This isotopic stability added to the experimental clarity and made the two-spot result robust across multiple trials. The historical context also helps explain why silver was chosen. During the early 1920s, researchers had limited access to highly specialized materials or advanced equipment. The practicality of obtaining pure, stable silver metal, combined with its physical properties, made it a sensible choice. The availability of silver ensured that the experiment could be conducted efficiently without excessive material difficulties. Its widespread use in industry and chemistry meant that high-purity samples were accessible, further reducing potential contamination or impurities that could affect the beam quality. Silver also played a role in reinforcing the simplicity of the experimental design. One of the remarkable features of the Stern-Gerlach experiment is its apparent elegance. A small furnace, a beam of atoms, a non-uniform magnetic field, and a detection plate. The simplicity of the apparatus made the experiment feasible for the time and allowed for clear interpretation of the results. Silver's suitability allowed the researchers to focus on the physics of the magnetic moment, rather than grapple with chemical, thermal, or material complexities that might have arisen with other elements. Additionally, silver's properties highlight the interplay between theoretical expectations and experimental design. Stern and Gerlach sought an atom where the magnetic effects could be isolated and measured directly. The single valence electron of silver provided an ideal system to observe the consequences of space quantization without confounding influences. In modern terms, one could think of this as designing a clean quantum system, where only the property of interest, spin, dominates the observable outcome. This foresight demonstrates a deep understanding of how to bridge theory and experiment, ensuring that the chosen element would produce unambiguous, interpretable results. The experiment also underscored the importance of matching atomic properties to available laboratory technology. The magnetic fields that could be generated in 1922 were limited in strength and precision. To observe measurable deflection, atoms needed a magnetic moment that could interact strongly enough with the available field. Silver's magnetic properties fit within this operational window, allowing the discrete deflection to become visible on the detection medium. Had the atom's magnetic moments been weaker, the splitting would have been too subtle, potentially lost in experimental noise. Conversely, atoms with excessively strong moments might have produced overly large deflections, complicating the interpretation. Silver struck the optimal balance. Another factor was the thermal behavior of silver. Heating atoms introduces random motion that can blur trajectories. Heavier atoms experience slower thermal velocities at a given temperature, reducing this blurring effect. Silver's mass ensured that the thermal spread of the atomic beam was sufficiently small to maintain a narrow, well-defined path through the magnetic field. This minimized experimental error and helped reveal the discrete splitting clearly. The interaction between atomic mass, thermal motion, and magnetic deflection exemplifies the careful considerations underlying the choice of silver. Silver's role can also be viewed through the lens of reproducibility and scientific rigor. Fundamental discoveries require evidence that can be replicated under similar conditions. The chemical and physical stability of silver allowed the Stern-Gerlach experiment to be repeated reliably, producing the same two-spot pattern consistently. This reproducibility was critical for convincing the scientific community that the observed quantization was real, not an experimental artifact. By using silver, Stern and Gerlach ensured that their results were robust, paving the way for widespread acceptance and further research into quantum phenomena. Moreover, silver atoms allowed the experiment to isolate the discrete effect of the quantum property that would later be identified as electron spin. At the time, the concept of spin was unknown, but the choice of silver naturally isolated the effect. Without complicating orbital contributions or multiple unpaired electrons, the deflection was clean and binary. This made the experiment a direct probe into the emerging concept of quantized angular momentum, setting the stage for subsequent theoretical developments. In essence, silver was the perfect probe for revealing nature's hidden quantum structure. Finally, the choice of silver symbolizes the integration of theory, experiment, and practical wisdom in scientific discovery. Stern and Gerlach could have attempted the experiment with other elements, but such attempts might have produced ambiguous results or introduced unnecessary technical challenges. By understanding the interplay of atomic structure, magnetic moment, experimental control, and detectability, they selected silver as the optimal medium to reveal quantum reality. This choice was instrumental in producing the clear, reproducible results that confirmed the discrete nature of atomic magnetic moments and ultimately changed the course of physics. In conclusion, silver atoms were used in the Stern-Gerlach experiment because they combined a single valence electron, minimal orbital angular momentum, suitable atomic mass, chemical stability, easy vaporization, visible detection, and isotopic simplicity. These properties ensured that the magnetic deflection would be measurable, interpretable, and reproducible. Silver's characteristics allowed the experiment to isolate the fundamental quantum effect of quantization, providing the first direct evidence of discrete spin states. Without silver, the experiment might have been inconclusive or technically unfeasible. Its use exemplifies the careful integration of theoretical insight and experimental pragmatism, demonstrating how the right choice of material can unlock profound discoveries about the fundamental nature of reality. The Stern-Gerlach experiment is famous for demonstrating the quantization of atomic magnetic moments, and the most striking visual evidence of this phenomenon was the splitting of the atomic beam into discrete parts. Understanding how the magnetic field split the beam requires examining both the physical interaction between atoms and magnetic fields and the quantum principles underlying these interactions. The splitting was not an arbitrary effect, nor was it the result of some classical force alone. It was a direct consequence of the quantized magnetic properties of atoms interacting with a specially designed inhomogeneous magnetic field. When silver atoms were heated in the furnace, they formed a beam traveling in a straight line toward a detection plate. Each atom carries a magnetic moment, primarily due to the intrinsic angular momentum, or spin, of its single valence electron. In classical physics, a magnetic moment can point in any direction, which would lead the beam to spread out continuously when exposed to a magnetic field. However, the key feature of the Stern-Gerlach experiment is that the magnetic field was inhomogeneous, meaning its strength varied along one direction. This inhomogeneity is essential because it produces a spatially dependent force on the magnetic moments. A uniform field would only tend to rotate or precess the atom's magnetic moments, producing no net deflection. The force acting on a magnetic dipole in a magnetic field is proportional to the gradient of the field in the direction of the dipole moment. Mathematically, this can be expressed as F equals mu b backslash math, F equals backslash nabla, backslash math, backslash mu backslash seed, dot backslash math b, F equals mu b, where mu backslash math backslash mu is the magnetic moment of the atom and b backslash math bb is the magnetic field. In the Stern-Gerlach setup, the field was designed so that there was a gradient along the vertical axis. Atoms whose magnetic moment pointed up experienced a force in the upward direction, while those whose magnetic moment pointed down experienced a force downward. The interaction between the inhomogeneous field and the discrete magnetic moments caused the atoms to follow different trajectories, resulting in spatial separation on the detection plate. The crucial point is that the magnetic moment of the atom is quantized. In the case of silver, the single unpaired electron behaves as if it has a spin of a half, which means its magnetic moment can only adopt one of two possible orientations relative to the magnetic field, up or down. There are no intermediate states. When the beam of atoms passes through the magnetic gradient, each atom is measured by the field, and it is forced into one of the two possible spin states. The force exerted on the atom depends on which orientation it assumes, and this difference in force is what physically splits the beam. The atoms that align with the up orientation are pushed upward, while atoms aligned with the down orientation are pushed downward. This produces the two distinct spots observed on the photographic plate. The geometry of the magnetic field is another essential factor. The poles of the magnet were shaped asymmetrically to create a strong gradient in one direction. One side of the pole was sharp and the other was flat, producing a difference in magnetic field strength over a small distance. This gradient ensures that even tiny differences in the orientation of the magnetic moment translate into measurable differences in force. Without a carefully designed gradient, the deflection would have been too small to observe, or the pattern would have been blurred. The beam splitting is therefore a direct consequence of both the quantization of the magnetic moment and the inhomogeneity of the magnetic field. It is also important to note that the silver atoms are electrically neutral. This fact eliminates the possibility that the splitting is due to electric charges interacting with the field. The only relevant interaction is between the magnetic dipole moment of the atom and the gradient of the magnetic field. This makes the experiment a clean demonstration of spin-dependent forces and ensures that the observed beam splitting directly reflects the quantum properties of the particles. In quantum mechanical terms, each atom in the beam exists in a superposition of spin states before entering the magnetic field. The inhomogeneous field effectively acts as a measurement device, collapsing the superposition into one of the two eigenstates. This is why the atoms do not deflect gradually or form a continuous distribution. Instead, they appear at discrete locations corresponding to the spin-up or spin-down state. The field does not force a random deflection. It selects one of the allowed quantized outcomes. This interaction illustrates one of the central principles of quantum mechanics. Measurement affects the system. The split beam is a visual manifestation of this principle. The magnitude of the splitting depends on several factors. The strength of the magnetic field gradient determines the size of the force on each atom. The mass and velocity of the atoms affect how much their trajectory changes over the distance to the detection plate. Thermal motion and beam collimation also play roles in ensuring that the two resulting beams remain distinguishable. In the Stern-Gerlach experiment, all these parameters were carefully controlled to ensure that the splitting could be observed clearly. The observed two-spot pattern confirmed that the magnetic field had successfully separated atoms according to their quantized spin states. The simplicity of the experimental setup belies the profound implications of the splitting. The fact that the beam divides into discrete components provides direct evidence that the magnetic moment of the atoms cannot take continuous values. Before this experiment, classical physics would predict a smooth smear on the detection plate because the magnetic moment could point in any direction. The observed splitting forced physicists to accept that quantum systems have discrete states, a fundamental departure from classical expectations. Furthermore, the Stern-Gerlach beam splitting has broader significance in understanding quantum measurement. The act of passing through the magnetic field does more than deflect the atoms. It forces each atom to choose a spin state. This process is essentially a quantum measurement, where the system collapses into one of its eigenstates. The magnetic field is not just a passive tool. It interacts with the atom in a way that fundamentally changes its quantum state. This insight laid the groundwork for later developments in quantum mechanics, including the formal theory of spin and the concept of qubits in modern quantum information science. Finally, the splitting of the beam illustrates the fundamental principle of space quantization. Each atom's magnetic moment aligns in discrete directions relative to the field, producing measurable, separate trajectories. This outcome is the earliest direct experimental evidence that properties of particles at the quantum level are discrete rather than continuous. The magnetic field's role in splitting the beam highlights the interplay between classical forces and quantum states. While the force itself can be described classically, the underlying quantization of the magnetic moment is purely quantum. The experiment is a perfect example of how quantum phenomena manifest in ways that are observable at a macroscopic scale, providing an elegant bridge between the microscopic world of atoms and the macroscopic world of experimental measurement. In summary, the magnetic field split the atomic beam in the Stern-Gerlach experiment because it interacted with the quantized magnetic moments of the silver atoms in a precisely engineered inhomogeneous field, each atom having a discrete spin state experienced a force proportional to the orientation of its magnetic moment relative to the field gradient. This force caused the atoms to follow different trajectories, resulting in two distinct spots on the detection plate. The inhomogeneous magnetic field was therefore the mechanism that converted the intrinsic quantum property of spin into a visible, measurable separation, providing the first direct evidence of quantization in atomic systems and revolutionizing our understanding of the microscopic world. The Stern-Gerlach experiment ultimately led to one of the most significant discoveries in quantum physics, the quantization of spin. While Stern and Gerlach themselves did not initially interpret their results in terms of electron spin, the concept had not yet been formulated. The experiment provided the first empirical evidence that particles possess an intrinsic form of angular momentum that exists in discrete states. The discovery of quantized spin not only explained the two-spot pattern observed in the experiment, but also opened an entirely new field of understanding in quantum mechanics, fundamentally altering how scientists perceive the microscopic world. Before the concept of spin was introduced, physicists understood angular momentum primarily in terms of orbital motion. Electrons orbiting the nucleus were expected to contribute to the atom's total angular momentum, which in turn determines its magnetic moment. Classical physics predicted that these angular momenta could take on a continuous range of values, leading to continuous magnetic orientations. The Stern-Gerlach experiment challenged this assumption directly. When a beam of silver atoms passed through an inhomogeneous magnetic field, it split into exactly two discrete components rather than forming a continuous smear. This result implied that some form of angular momentum existed in the atoms that could only take discrete values, either up or down, and that no intermediate orientations were possible. The immediate implication was that there was an intrinsic property of the atom responsible for the observed quantization. At the time, scientists referred to this as space quantization, a term indicating that the orientation of angular momentum in space could only occupy certain discrete directions. However, the precise origin of this quantization was unknown. The outermost electron in silver atoms contributes very little orbital angular momentum in the ground state, so the splitting could not be explained by orbital motion alone. The experiment demonstrated that the electron itself must carry an additional form of angular momentum independent of its orbital motion. This property would later be recognized as spin. In 1925, a few years after the Stern-Gerlach experiment, Samuel Goudsmit and George Uhlenbeck proposed the idea of electron spin to explain anomalies in atomic spectra and the observed splitting patterns of atomic beams. They suggested that electrons behave as if they are spinning around their own axis, generating an intrinsic magnetic moment. Unlike orbital angular momentum, which arises from electrons moving around the nucleus, spin is an inherent quantum property of the electron itself. It cannot be visualized classically, and its magnitude is fixed. For electrons, the spin quantum number is s equals 12 equals \frac 1, 2, s equals 21. This intrinsic spin directly explains why the Stern-Gerlach experiment observed only two deflection paths. The magnetic moment associated with spin can align either parallel or antiparallel to the magnetic field gradient, producing the discrete up or down outcomes. The discovery of quantized spin resolved several long-standing questions in physics. One major puzzle was the fine structure observed in atomic spectra. When scientists examined spectral lines with high precision, they noticed that certain lines were split into multiple components, a phenomenon that could not be explained by orbital angular momentum alone. the introduction of spin provided a natural explanation. The intrinsic spin of electrons interacts with their orbital motion, giving rise to what is known as spin-orbit coupling, which produces the observed spectral splitting. Thus, the Stern-Gerlach experiment provided not only direct evidence of discrete spin states, but also the foundation for understanding complex atomic structures. Quantized spin also has profound implications for the behavior of multiple electrons in atoms. According to the Pauli exclusion principle, no two electrons in an atom can occupy the same quantum state simultaneously. Spin is a critical component of this principle. Electrons can occupy the same orbital as long as their spins are opposite. This explains the arrangement of electrons in shells and subshells and accounts for the chemical properties of elements. In other words, the discovery of quantized spin is not merely a curiosity of particle physics. It is central to the entire structure of matter and chemistry. The Stern-Gerlach experiment also demonstrated a remarkable property of spin. It is intrinsically quantized, unlike classical angular momentum, which can vary continuously. Each electron's spin is limited to two possible projections along any chosen axis, which is why the silver beam splits into two discrete components. This quantization is absolute and does not depend on the choice of magnetic field strength or orientation, though the measurement axis does determine which projection is observed. This insight is fundamental to quantum mechanics. Particles have intrinsic properties that are discrete, measurable, and independent of classical intuition. It is worth noting that the discovery of spin introduced the idea of non-classical angular momentum. Spin cannot be understood as literal rotation in space. If an electron were a tiny sphere spinning physically, its surface would move faster than the speed of light, which is impossible. Instead, spin is a purely quantum property, manifested through its magnetic moment and its interactions with magnetic fields. The Stern-Gerlach experiment made this abstract concept observable. The magnetic deflection of silver atoms translated the hidden quantum property of spin into a macroscopic effect. Quantized spin also introduced the concept of superposition in a very tangible way. Before entering the magnetic field, each silver atom's spin is in a superposition of up and down states along the measurement axis. Only when the atom interacts with the inhomogeneous magnetic field does the spin collapse into one of the allowed eigenstates, producing a measurable deflection. The splitting of the beam into two discrete spots is therefore a direct manifestation of quantum measurement. The magnetic field does not create spin. It reveals which quantized state the electron occupies. This idea became a cornerstone of quantum theory, demonstrating that measurement is not a passive act, but an interaction that fundamentally affects the system. The discovery of quantized spin also laid the groundwork for technological innovations. Spin is the basis for magnetic resonance imaging MRI, which exploits the alignment of nuclear spins in a magnetic field to produce detailed images of the human body. In modern physics, electron spin is used in spintronics, where information is encoded in the spin state of electrons rather than their charge, potentially enabling faster and more efficient electronics. Quantum computing relies heavily on spin as a physical realization of qubits, the fundamental units of quantum information. All of these technologies trace their conceptual roots back to the original discovery of quantized spin, first made observable by the Stern-Gerlach experiment. In essence, the discovery of quantized spin represented a radical departure from classical physics. It revealed that electrons, and indeed all fundamental particles, carry intrinsic angular momentum that is discrete, directional, and quantifiable. The Stern-Gerlach experiment provided the first direct experimental evidence of this phenomenon, showing that particles do not behave as classical objects, but instead follow the counterintuitive rules of quantum mechanics. The beams, splitting into two distinct components, offered a clear, visual confirmation that spin exists and is quantized, providing a bridge between abstract theory and experimental observation. In conclusion, the discovery of quantized spin emerged from the Stern-Gerlach experiment's unexpected observation of a split atomic beam. This splitting could not be explained by classical orbital motion alone, and pointed directly to the existence of an intrinsic form of angular momentum carried by electrons. The concept of spin explained the two-spot pattern, resolved anomalies in atomic spectra, underpinned the Pauli exclusion principle, and introduced superposition and measurement effects central to quantum mechanics. Moreover, spin's discovery laid the foundation for numerous modern technologies, from MRI to quantum computing. The quantization of spin represents a profound insight into the fundamental structure of matter and remains one of the most important discoveries in the history of physics, directly linking the microscopic quantum world to observable macroscopic phenomena. The Stern-Gerlach experiment not only revealed the existence of quantized spin, but also fundamentally challenged classical physics, shaking the foundations of the Newtonian world, that had dominated science for centuries. Classical physics is based on principles of continuity, determinism, and predictability. Objects in the classical world follow precise trajectories, forces produce proportional motion, and physical quantities such as energy and angular momentum can vary smoothly over a continuous range. The results of the Stern-Gerlach experiment confronted each of these assumptions, demonstrating that at the atomic level, the behavior of matter is governed by discrete, probabilistic, and non-intuitive rules that classical physics cannot explain. In classical terms, the magnetic moment of an atom should behave like a tiny bar magnet or spinning top. A bar magnet placed in a non-uniform magnetic field experiences a force proportional to its orientation relative to the field. Since a classical magnet can point in any direction, a beam of such magnets passing through the field should spread out continuously, forming a smear on a detector. This prediction arises naturally from classical mechanics. Forces vary continuously, and angular momentum is not restricted to discrete values. Stern and Gerlach expected, based on classical physics, that the silver atom's magnetic moments would produce a continuous distribution of deflection. Yet, when they ran the experiment, the results were starkly different. Instead of a continuous smear, the beam split into two distinct spots. This observation directly contradicted the classical prediction. The atoms behaved as if their magnetic moments could only point in one of two directions along the axis of the magnetic field gradient. Classical physics offered no mechanism for this behavior. There was no reason, within the Newtonian framework, why a magnet could only align in discrete orientations rather than any orientation in space. The splitting demonstrated that angular momentum is quantized, a concept alien to classical understanding. The experiment also challenged the classical assumption of determinism. In Newtonian mechanics, if one knows the initial conditions of a system, the position, velocity, orientation, and forces acting on it, the future trajectory is completely determined. For the Stern-Gerlach experiment, classical physics would predict that knowing the initial orientation of an atom's magnetic moment would allow one to determine exactly how it would deflect. However, the quantum reality revealed by the experiment is fundamentally probabilistic. Atoms with identical initial conditions do not all deflect in the same direction. Each atom has a 50% chance of going up and a 50% chance of going down, regardless of its prior orientation. This indeterminacy cannot be explained by classical physics, which assumes that nature operates like a clockwork mechanism where outcomes are fully predictable. The Stern-Gerlach experiment also challenged classical physics conceptually by introducing the notion of measurement influencing reality. In classical mechanics, observing a system does not alter its behavior in any fundamental way. One can measure position, momentum, or orientation without affecting the system. In the Stern-Gerlach experiment, however, the act of passing through the inhomogeneous magnetic field forces each atom into one of the allowed quantized states. Before entering the field, the atom's spin can be thought of as existing in a superposition, a combination of up and down states. The magnetic field interaction constitutes a measurement that collapses this superposition into a definite outcome. This phenomenon, where the act of observation determines the physical state, is completely foreign to classical physics and represents a profound departure from its assumptions. Another classical assumption challenged by the experiment was continuity of physical quantities. In classical electromagnetism, quantities such as energy, angular momentum, and magnetic moment vary smoothly. Any orientation of a spinning electron or atom should be allowed, producing a continuous range of forces in a magnetic field. The discrete splitting of the silver beam demonstrates that these quantities are inherently quantized at the microscopic scale. The atomic world does not obey the smooth, continuous rules of classical mechanics. Instead, nature is chunky. At the quantum level, with angular momentum existing in indivisible units, and magnetic moments restricted to discrete orientations. Furthermore, the experiment confronted classical intuition about space and geometry. Classical physics suggests that objects exist in three-dimensional space and can point or rotate in any direction freely. The Stern-Gerlach experiment revealed that angular momentum behaves differently. It is restricted to specific projections along a chosen axis. This is called space quantization, and it is entirely non-classical. An atom does not have an orientation that can be measured in all directions simultaneously. Instead, measurement along one axis produces discrete outcomes, and different measurement axes can yield different results. This violated the classical expectation that a system's angular momentum should be a continuous vector in three-dimensional space. The experiment also called into question the classical notion of hidden variables. Some physicists initially attempted to explain the beam splitting by assuming that the atoms had hidden, unmeasured orientations, which would determine the deflection in a deterministic way. However, later theoretical work, particularly Bell's theorem in the 1960s, showed that no local hidden, variable theory can fully account for quantum outcomes. The Stern-Gerlach experiment provided early evidence that quantum mechanics cannot be reduced to classical deterministic models with unknown parameters. Its results implied that nature at the atomic scale is fundamentally probabilistic, not merely unknowable due to experimental limitations. Moreover, the experiment highlighted the failure of classical mechanics to account for intrinsic particle properties. In classical physics, angular momentum arises solely from motion through space. An object must rotate or orbit to have angular momentum. Electrons, however, possess intrinsic spin, which contributes to angular momentum independently of any spatial motion. The discrete splitting observed in the Stern-Gerlach experiment was the first direct evidence of this intrinsic property. Classical physics had no framework for understanding spin as a non-orbital, intrinsic quantity. So the experiment exposed a critical limitation of classical theory. The broader implication of the experiment is that classical physics is a limiting case of quantum physics, valid only for macroscopic systems. For everyday objects, angular momentum appears continuous, trajectories are predictable, and measurement does not fundamentally disturb the system. However, at the atomic level, the Stern-Gerlach experiment revealed that these assumptions break down. Quantization, superposition, and probabilistic outcomes dominate, and the rules of classical physics are no longer adequate. This insight forced physicists to rethink the foundations of mechanics and led directly to the development of modern quantum theory, which replaced classical determinism with a probabilistic framework governed by wave, functions, and operators. Finally, the experiment challenged the classical view of observation and reality. In classical mechanics, reality is objective and independent of measurement. The Stern-Gerlach experiment demonstrated that, at the quantum level, reality is not fully determined until a measurement is made. The orientation of the electron's spin becomes definite only when the atom interacts with the magnetic field. This departure from classical objectivity was deeply unsettling to many physicists, including Einstein, who famously resisted the idea of inherent probabilistic behavior in nature. Nevertheless, the experiment's results left no doubt. Classical physics could not account for atomic phenomena. In conclusion, the Stern-Gerlach experiment challenged classical physics in multiple ways. It showed that angular momentum is quantized rather than continuous, that outcomes at the atomic level are probabilistic rather than deterministic, and that measurement fundamentally affects the system being observed. It revealed intrinsic particle properties, defied classical intuitions about space and motion, and provided a direct experimental demonstration of quantum behavior that classical theory could not explain. The experiment forced a paradigm shift in physics, marking the beginning of the quantum era and demonstrating that classical physics, while accurate for macroscopic systems, is fundamentally inadequate for describing the microscopic world of atoms and electrons. The Stern-Gerlach experiment played a pivotal role in shaping the development of quantum mechanics, fundamentally altering the trajectory of 20th century physics. By providing the first direct experimental evidence of quantized angular momentum, the experiment offered a concrete observation that challenged classical physics and guided theorists toward a more complete understanding of the microscopic world. Its influence is seen not only in the development of spin theory, but also in the broader, conceptual framework of quantum mechanics, including the notions of quantization, superposition, measurement, and the probabilistic nature of physical reality. Before the Stern-Gerlach experiment, quantum theory was largely theoretical and abstract. Max Planck had introduced quantized energy levels in 1900 to explain blackbody radiation, and Niels Bohr had proposed discrete electron orbits in 1913 to account for the stability of atoms and the emission spectra of hydrogen. While these ideas successfully explained certain phenomena, they were still constrained by classical intuition and lacked direct experimental verification at the level of atomic angular momentum. The Stern-Gerlach experiment provided a concrete, observable demonstration of quantization, confirming that certain properties of atoms, such as magnetic moments associated with angular momentum, not vary continuously but exist only in discrete states. This empirical validation helped solidify the emerging quantum framework and inspired confidence in the nascent theory. One of the most significant contributions of the experiment was its direct evidence for quantized spin. By passing a beam of silver atoms through an inhomogeneous magnetic field. Stern and Gerlach observed that the beam split into two distinct components. This splitting could not be explained by orbital angular momentum alone, particularly since silver atoms in the ground state have negligible orbital contribution. The observed two-spot pattern implied the existence of an intrinsic angular momentum for the electron, which could adopt only two discrete orientations relative to the measurement axis. This concept of intrinsic quantized spin became a cornerstone of quantum mechanics. Without this experimental observation, the notion of spin might have remained a purely theoretical hypothesis for much longer. The experiment also played a key role in advancing the matrix mechanics and wave mechanics formulations of quantum theory. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, among others, were developing mathematical frameworks to describe the behavior of quantum systems. The discrete outcomes observed in the Stern-Gerlach experiment exemplified the need for operators and eigenvalues in these frameworks. Spin, being inherently quantized, could not be described by classical vectors, but required a formalism in which observables correspond to operators acting on quantum states, with measurable outcomes corresponding to eigenvalues. The two distinct deflections of the atomic beam provided a physical manifestation of this abstract mathematical structure, helping bridge theory and experiment. Another profound impact of the experiment was its role in illustrating the principle of superposition. Before passing through the magnetic field, each silver atom can be thought of as being in a superposition of spin-up and spin-down states. The inhomogeneous magnetic field acts as a measurement device, collapsing this superposition into one of the allowed eigenstates. This was one of the earliest experimental examples of quantum superposition being directly observed. The clear binary outcome, two spots on the detector, demonstrated that quantum states exist as combinations of possibilities that become definite only upon measurement. This principle underlies much of modern quantum mechanics and informs our understanding of phenomena such as entanglement, quantum tunneling, and quantum computing. The Stern-Gerlach experiment also helped establish the concept of space quantization, a critical foundation for later quantum theory. Classical physics predicts that angular momentum can point in any direction, but the experiment showed that only specific orientations along the measurement axis are allowed. This discovery forced physicists to adopt a new perspective. At the atomic level, physical quantities are restricted to discrete eigenstates, not continuous ranges. This principle became central to the theory of atomic structure, spectroscopy, and quantum angular momentum. It also provided the experimental basis for understanding phenomena such as the Zeeman effect, where spectral lines split in the presence of a magnetic field, and spin-orbit coupling, which influences the fine structure of atomic spectra. The implications of the experiment extended beyond individual particles to the broader statistical and probabilistic nature of quantum mechanics. Classical physics assumes determinism. Given precise knowledge of initial conditions, one can predict the future state of a system exactly. The Stern-Gerlach experiment demonstrated that even with identical initial conditions, individual atoms exhibit probabilistic outcomes when measured. Half the silver atoms deflected upward and half downward, with no way to predict the path of any single atom. This probabilistic behavior highlighted the necessity of a new theoretical framework, quantum mechanics, that describes the likelihood of outcomes rather than deterministic trajectories. It directly influenced Heisenberg's uncertainty principle, Schrödinger's wave function formalism, and Born's statistical interpretation of quantum mechanics. Furthermore, The experiment influenced the development of quantum measurement theory. In classical physics, measurement is passive, revealing pre-existing properties without altering the system. The Stern-Gerlach experiment demonstrated that measurement interacts with the system in a fundamental way. The atom's spin state is undefined until it passes through the magnetic field, which acts as a measurement apparatus. This early insight into measurement disturbance helped shape discussions about the role of observation in quantum mechanics and the philosophical implications of quantum theory, which continue to be debated today in the context of the measurement problem and interpretations of quantum mechanics. The experiment also had practical implications for atomic and particle physics. By demonstrating that intrinsic properties like spin are quantized, it paved the way for the classification of particles according to spin, leading to the development of fermions and bosons. Foundation of quantum statistics. The distinction between half-integer and integer spins, derived from observations like the Stern-Gerlach splitting, is critical for understanding the Pauli exclusion principle, atomic structure, and the behavior of matter at both microscopic and macroscopic scales. In short, the experiment directly contributed to the development of the rules that govern all quantum particles. Finally, the Stern-Gerlach experiment served as a bridge between abstract theory and observable reality. Quantum mechanics is often criticized as being mathematically complex and counterintuitive. The visual splitting of a beam of atoms into two discrete spots provided a tangible, observable effect of quantization, connecting theory with experiment in a way that was both compelling and undeniable. This experimental grounding helped legitimize quantum mechanics in the eyes of the scientific community and encouraged further theoretical and experimental exploration, shaping the trajectory of physics throughout the 20th century and beyond. In conclusion, the Stern-Gerlach experiment's role in shaping quantum mechanics cannot be overstated. By revealing the quantized nature of spin, demonstrating superposition, establishing space quantization, and illustrating the probabilistic nature of measurement, the experiment provided essential empirical support for the emerging quantum theory. It bridged theory and observation, influenced the mathematical formulation of quantum mechanics, guided the understanding of atomic and particle behavior, and highlighted the fundamental departure of the microscopic world from classical expectations. The experiment did not just confirm existing ideas, it defined the experimental foundation upon which modern quantum mechanics was built, influencing both conceptual understanding and practical applications, and setting the stage for the technological and scientific advances that continue to shape our world today. The Stern-Gerlach experiment, first conducted in 1922, was a groundbreaking demonstration of the quantized nature of atomic properties, specifically electron spin. While its immediate significance was in confirming the existence of discrete spin states and advancing the foundations of quantum mechanics, its long-term impact extends far beyond theory. The experiment's insights have become cornerstones for modern quantum technologies, influencing everything from magnetic resonance imaging MRI to quantum computing, spintronics, and quantum communication. Understanding this impact requires tracing how the discovery of quantized spin and its experimental validation have shaped technological innovations in the century that followed. One of the most direct applications of the Stern-Gerlach experiment is in magnetic resonance technologies, particularly MRI. MRI relies on the alignment of nuclear spins in a magnetic field to generate highly detailed images of soft tissues within the human body. The principles of spin quantization and magnetic moment, first evidenced in the Stern-Gerlach experiment, are directly applied in this technology. In MRI, nuclei such as hydrogen protons have intrinsic spin, which behaves in a manner analogous to the spin of electrons in silver atoms. When placed in a strong external magnetic field, these spins align with or against the field, creating distinct energy levels. Radio frequency pulses then perturb this alignment, and the system's relaxation produces measurable signals. Without the experimental verification of discrete spin states provided by Stern and Gerlach, the theoretical understanding necessary for MRI might have developed more slowly, delaying this transformative medical technology. The experiment also laid the conceptual groundwork for Spintronics, an emerging field in condensed matter physics and electronics. Unlike conventional electronics, which rely solely on the charge of electrons to carry information, Spintronics exploits the electron's intrinsic spin to encode and manipulate information. Devices such as spin valves, magnetic tunnel junctions, and spin-based transistors all depend on controlling the spin state of electrons. The discrete nature of spin, first observed in the Stern-Gerlach experiment, enables precise manipulation, switching, and storage of information in ways that classical charge-based electronics cannot achieve. Spintronics has enabled advancements in high-density memory storage, non-volatile memory technologies, and energy-efficient electronics, demonstrating a clear technological lineage from the principles revealed in the experiment. Another crucial area influenced by the Stern-Gerlach experiment is quantum computing. Quantum computers leverage qubits, which are two-level quantum systems, to perform calculations that would be infeasible for classical computers. Electron or nuclear spin states often serve as physical realizations of qubits, directly reflecting the up and down outcomes observed in the Stern-Gerlach experiment. Superposition allows qubits to exist in a combination of these states, enabling parallel computation and enormous speedups for certain algorithms. The foundational understanding of spin as a discrete quantum property, validated by the Stern-Gerlach experiment, provides the essential physics for designing, controlling, and measuring qubits. In this sense, the experiment did not merely confirm a theoretical concept. It provided a blueprint for the technologies underpinning the next computing revolution. Quantum communication technologies also trace their roots to the Stern-Gerlach experiment. Quantum key distribution, QKD, and other secure communication protocols rely on the manipulation and measurement of quantum states, often encoded in spin or polarization. The discrete, binary nature of spin makes it ideal for encoding information in a way that is fundamentally secure. Any measurement of a quantum state collapses it, revealing potential eavesdropping. The experiment's demonstration of discrete spin states provided the first empirical evidence that such binary quantum states exist and are reliably measurable, a prerequisite for the development of quantum cryptography. Without this foundational knowledge, designing practical quantum communication systems would be far more challenging. The Stern-Gerlach experiment also influenced precision measurement and quantum metrology. Modern atomic clocks, which are the backbone of global positioning systems and international timekeeping, rely on transitions between discrete quantum states. These transitions often involve spin-dependent interactions, making the understanding of quantized spin critical for accuracy. Similarly, devices that measure magnetic fields at extremely small scales, such as SQUIDs, superconducting quantum interference devices, exploit spin interactions. By validating the existence of discrete spin states and their controllable response to magnetic fields, the Stern-Gerlach experiment provided the experimental framework for these ultra-precise measurement techniques. In addition, the experiment's influence extends to fundamental research in quantum mechanics and particle physics, which indirectly drives technological innovation. Understanding spin has been crucial in classifying elementary particles as fermions or bosons, predicting their statistical behaviors, and exploring phenomena like superconductivity, superfluidity, and topological materials. These areas of research are not purely theoretical. They inform materials science, electronics, and emerging quantum devices. For instance, quantum materials designed for spintronic devices or topological, quantum computers rely on principles directly connected to the discrete spin states, first evidenced by Stern and Gerlach. The educational and conceptual impact of the experiment is equally important for technology. The Stern-Gerlach experiment provides a clear, visual illustration of quantum principles, making abstract concepts like superposition, measurement, and quantization tangible. By offering a concrete demonstration of spin, the experiment has become a central teaching tool in physics education, inspiring generations of scientists and engineers who go on to develop quantum technologies. Its role in shaping the way scientists think about and manipulate quantum systems has accelerated innovation across multiple technological domains. It is also worth noting that the experiment has inspired modern experimental techniques. Atomic beam manipulation, spin filtering, and magnetic deflection methods used in contemporary laboratories trace their conceptual lineage to the Stern-Gerlach setup. Techniques for isolating, controlling, and measuring quantum states in a controlled environment are essential for quantum sensors, quantum simulators, and research into entangled systems. By demonstrating that atomic and subatomic properties could be manipulated and measured with precision, the Stern-Gerlach experiment set the stage for a wide array of experimental tools and technologies. Finally, the experiment highlights the importance of bridging fundamental physics and practical applications. While the original goal was to explore the nature of atomic magnetic moments and test theoretical predictions, the results provided insights that now underpin technologies affecting everyday life, from medical imaging to secure communication and computing. This trajectory underscores a key lesson of scientific progress. Fundamental discoveries, even when initially abstract, often have profound and unexpected technological consequences. The Stern-Gerlach experiment exemplifies this principle, demonstrating how an experiment designed to probe the deepest mysteries of quantum behavior can catalyze innovations that transform society. In conclusion, the Stern-Gerlach experiment's impact on modern quantum technologies is vast and multifaceted. By revealing the discrete, quantized nature of spin, it laid the foundation for MRI and other medical imaging technologies, enabled spintronics and high-density data storage, provided the basis for qubit design in quantum computing, and supported secure quantum communication systems. It influenced precision measurement, quantum metrology, and the study of quantum materials, while also shaping experimental techniques and physics education. The experiment not only validated the fundamental principles of quantum mechanics, but also demonstrated their practical relevance, showing that the quantum world, once thought abstract and inaccessible, could be harnessed to drive technological innovation. Its legacy continues to guide research and development, ensuring that the insights from a single beam of silver atoms nearly a century ago remain central to the rapidly evolving field of quantum technology today.